We have a couple of handouts here that if you, hopefully everybody's gotten them on the way in. The first handout is handout number 3, which is basically a summary of all the formulas. If I, oh, you have the overhead for a second, TV. Right here. This should be all stuff that looks fairly familiar to you. Actually, we're going to talk about the gap later today, but that part under number 2 at the bottom. But anyway, grab onto this. This is a nice summary, kind of convenient to use. Gives you the relationship between the various parameters for the PAM constellations and the QAM constellations. You get the probability of error expressions, probability of bit error, expression B bar, EX, D min, and such, and the interrelationships between them. So kind of a nice summary rather than having to dig through the chapter and find all this or try to memorize it or whatever. So you may find that useful. And then the other handout, of course, problem set number 1 is turned off at this point, so no more late homework on problem set number 1. And these are the solutions for that, so you can go ahead and use that as you like to study. Does anyone have any questions that may have come up, any issues? I have one that Edward asked me to put on that's come up in some of the help sessions and office hours that he's been running, and that has to do with the translation property. You recall, I think it was about 2 or 3 lectures ago, we talked about if we had any constellation. Let me give you a little example here. I'll just draw one on screen, kind of impromptu, of, let's say we have a little 4-point QAM there. So this is one constellation, and then we have something that looks like this. If these two constellations, this one up here is actually translated and rotated, but the translation of this constellation, the optimum detector performs the same. It has the same probability of error. That does not mean that the argument of the Q function in terms of relationship to signal-to-noise ratio is necessarily the same. But because this constellation is a translation of that one plus a rotation, the probability of error is the same. This one needs a lot more energy, okay? But the probability of error for the optimum detector is still the same. Given these two constellations, if you can recognize that one is a translation, rotation of the other, get the same probability of error. This one's clearly better, but same probability of error. Yes, ma'am?
How would you define the SNR in the case of the translation?
Well, it's kind of ugly because we're going to get a really high signal-to-noise ratio in this case because there's a lot of energy. So it may not be a particularly good measure of performance because the choice of constellation is relatively poor. If we were to go ahead and make fair comparisons for this particular system, we would see that the EX bar, you know, for instance, if we kept the probability of error the same and the B bar the same, which they are, the EX bar for this constellation is a lot higher than it is for this one, so it's poorer in that sense. It uses more energy to get the same performance. So the fair comparisons still work, but the signal-to-noise ratio itself it becomes a little bit of a confusing quantity when you have unusual constellations like this. When you're doing nice packing around the origin, you don't have any DC offsets, which clearly this constellation does. It has a constant in it. That's the translation, actually, which is kind of useless energy because it's the same for all points transmitted and just simply causes us to use more energy to transmit the signal with no improvement in performance. But nonetheless, given the fact that they are different constellations, they have the same TE bar, the same B bar, but they have different EX bars. So by our rules of fair comparison, this one's better in this case. So don't confuse the translation property to say that you have to have the same expression for probability of error. You just have the same performance of an optimum detector, whatever the expression for probability of error may be. Okay. All right. That help a little? Okay. I have no other issues or questions that anyone has raised at this point. So what I'd like to do is I got a couple of things that I'm going to do today, kind of finish off the QAM part of the class. Let me give you the outline by going through a few examples. I have really done about all I want to do from Chapter 1, except for the gap approximation, which I'm going to talk about on the second bullet item today. Then we're going to move into Chapter 2, which is passband signals, and we'll probably cover passband channels today also. They're right at the beginning of Chapter 2. What we'll do more of there, I'm going to come back to section 1.7 a little bit later as we proceed. It has to do with the case of noise that's no longer white, still Gaussian, still added in the channel, but no longer white. And basically the trick in that case is you go through some kind of transformation in your receiver that whitens the noise, and then that transformation changes the signals that are transmitted, so you get a different D-min, get different performance in that case. But then you have an optimum detector. Why? Because of the reversibility theorem. As long as we go through a one-to-one transformation in whitening the noise, then we haven't changed the performance of the optimum detector in that case. So we're going to come back to that after we understand a little bit more about passband channels and intersymbol interference. It'll make more sense at that point, the discussion of any colored noise. So what I'm going to do here is not so much in the book itself. The gap approximation is in sections it's in 1.6 of the lecture notes. It's discussed a little bit there, but it's a pretty easy concept. We're going to visit that. I'm going to talk about some examples, and in fact we have a VCR tape that seems to be pretty popular with the students. About 10 years old, but some 379A students many years ago went out to work at a company called Applied Signal Technology out in the Valley, which is kind of a defense contractor who does modem designs for various parts of the military. And they made a little tape of QAM performance and such, which always is pretty popular with the students. So hopefully the VCR tape hasn't been, I haven't used it since last year, so I hope it hasn't erased itself by sitting on the shelf this long. So we're going to take a look at that today also. But let me start with a few examples before I dive into that tape. What I'd like to do under examples is just tell you a few places where QAM is used. As I said earlier, this is probably the most heavily used transmission format. Even if the system doesn't say specifically that it uses QAM, it's usually constructed maybe from multiple QAM signals in some kind of form. So typically, I think we could say almost without a doubt that it's the most heavily used transmission technique. I'll start just briefly by mentioning PAM, which is probably second most heavily used technique, but not nearly as often. And in the case of just bipolar or 2 PAM transmission, you'll see that basically this is used very often in disk drives for modulation. You can think of the write process where you write messages on a disk as similar to a transmitter. It is. And because of the magnetics involved in the disk storage channel, you can only have north-south or south-north, so you get plus or minus 1 basically in that system. So two-level PAM is used very heavily in the storage industry with something we call partial response signaling, which we'll see a little bit later in Chapter 3. It's also the very early Ethernet systems. So if you have an older one that transmits at 10 megabits per second or falls back to transmit at 10 megabits per second, but talking to an old router, you'll see that that actually is also binary PAM transmission. Probably the most popular PAM that I know of today, and many of you probably own one of these, you certainly own a disk drive also, but it's a so-called V.90 or V.92 voice band modem. So you buy a portable laptop computer, you buy your desktop computer, and it's got a modem just in case, a voice band modem, just in case you don't have DSL, you don't have cable modem or Wi-Fi or some other type of connection, you'll dial up and use that. And these modems run at 56 kilobits per second over normal dial-up connections. And basically, what is transmitted on these systems is 128 PAM. So you actually see 7 bits per symbol. There's a very high signal-to-noise ratio in the channel, so you can get 7 bits per symbol. So B is equal to 7, and 1 over T is equal to 8,000 hertz. So basically that gives you a data rate R of 56 kilobits per second. How do we get that? Well, it's B over T. So 7 times 8,000 is 56 kilobits per second. The actual signal constellation, I should mention, unfortunately deviates a little bit from what I taught you, in that the points in the middle are more closely spaced and they gradually get further apart as you go out from the center. Now, why would they do that? Why would they change the D-min? It turns out that the channel has a nonlinearity in it that has to do with the voice compression that's used in the transmission network itself. And so, in effect, because of that compression, when you finally get to the receiver, these look like they're equally spaced. But when they're launched, they're not equally spaced. The compression system tends to allocate more precision in transporting voice to very small signals than it does to larger signals, and so they basically pre-warp the transmission signals, if you will, and what happens when you come out is you get equally spaced levels from that. So that's an example of PAM also. Now QAM, as I mentioned, much more heavily used, and in fact this 56 kilobits per second, if you actually read the details on your modem link, it's only going in the direction out towards the actual modem in your computer. The opposite direction uses a different type of modulation, and it is sometimes called V.34. It's the same thing in the V.90 standards, and it's QAM, and the number of bits is 9 bits per symbol. The symbol rate is 3,200 hertz. Now remember, we got 2 dimensions here, so this is more like 6,400 dimensions per second in QAM, comparing to this 8,000 dimensions per second in the 56K modem. And what that works out to be is, if you take the 9 times 32, basically what you get is 28.8 kilobits per second being transmitted. Okay. Now clearly we're going to need a pretty high signal-to-noise ratio for this. Not as high as PAM, because PAM it's 7 bits per dimension. Here it's 9 bits, but it's over 2 dimensions, so that's 4.5 bits per dimension. So actually the PAM system needs yet a higher signal-to-noise ratio here for this 56 kilobit per second transmission than you need for the 28.8 kilobit per second. And if you look at the difference in data rates, that does indeed make some sense that would be the case. How does this actually work on a voice band channel? The voice band channel itself looks something like this, where basically it passes signal energy. I'm going to put 320 hertz, but roughly from 300 hertz up to about 3,000 hertz. I'm going to put 3120 here. There's actually a carrier frequency. Remember, I talked about some kind of carrier frequency being used, so we modulate the signals away from DC. And the channel basically looks like this, the voice band modem channel. Now, it may not be perfectly flat through here. It may slope off a little bit, but basically it passes energy in this region. So the modulation basis functions are designed, okay, with 3,200 hertz. If I look at the sync function, let's say, that would have a bandwidth from minus 1,600 hertz to 1,600 hertz. And then if I have a carrier frequency of 1920, what happens? Well, I add 1920 to 1,600, and then I subtract 1,600 from 1920. When I subtract, I get 320 hertz. And so I get the 2 upper and lower edges of the thing. That's what the multiplication by cosine does. It gives us sum and differences translations of the original baseband signal. So this is roughly correct than the basis function. You get a basic idea, without going through all the details, that you by now well know how to do for the individual basis set, that makes some sense. It's a reasonable match. Now, a question some of you might have will say, just 56 kilobits per second, why are they using PAM on a channel that doesn't pass DC here? Okay, isn't that kind of stupid, Professor Cioffi? And in a way it is, okay, because it's not a very good match to the channel itself. But they have a very, very powerful equalization method that attempts to make this channel look flat again at all frequencies, even down at DC, called decision feedback equalization. And we are going to see decision feedback equalizer about halfway through chapter 3 of how to correct on this channel. So this QAM system is a little easier to use, and it kind of just stitches the basis functions in the same frequency band that is being passed by the channel, so it's a little easier type of design. This other system uses a very sophisticated technique that basically changes the channel and pulls out whatever tiny signal energy might be down here at the lower frequencies and up here at the higher frequencies all the way up to 4,000 hertz, and tries to take advantage of that. So we'll see it a little bit later. So there's an example of QAM. A third example of QAM is in cable modems. So if you happen to get your internet traffic over the cable system, you have a couple of directions. One is the transmitted signals to you, and of course the other direction is the signals that you transmit back up to the cable system head end, and then there's a connection router to the internet at that side. If you actually look at the frequency plan of your coaxial cable TV system, basically legacy reasons, they have analog TV, either that or they've replaced it by digital TV, but it's in the same frequency band, which starts around 50 megahertz or so. In fact, if you happen to know, in the United States, the carrier frequency for channel 2 is 52 megahertz, and every 6 megahertz thereafter is channel 3, channel 4, and so forth as they go up. And these signals are just maintained there, okay, without change. Those are the same old TV signals that have always been there. And where they send the other direction upstream from your modem towards the cable head end is below this 40 megahertz, below the TV signals. Basically, they start around 5 megahertz and get up to about 40 or so, and they put QAM signals there. Now, the QAM signals in this case have typically a symbol rate of 2 megahertz, or roughly 2 megahertz, and B is equal to 2. There's a lot of noise in this band coming up. So the original cables were not designed to transmit upstream. They were just sending broadcast television. So it's not a pretty picture down there. There's all kinds of noise that leaks into the system. They didn't care when they were installing this because they're going to put TV way up here. So it's got a bad signal to noise ratio. So they can't send a lot of points in the QAM constellation. Some advanced systems try to get a few more than 2 bits per symbol, but it's not particularly easy. And they have, with a symbol rate of 2 megahertz and various carrier frequencies, say like 10, 12, 14 megahertz in this region, they have these bit streams which are basically 4 megabits per second. Now usually these bit streams, okay, you can see here 2 times 2 is 4 megabits per second. So you see them in there. We may have more than one of them. These 4 megabit bit streams are actually shared. Okay, so if you're not using it and your neighbor's on the system because he's in the same 5 to 40 megahertz band, okay, maybe 30 to 50 customers will share a single frequency, another 30 to 50 customers will share a different frequency, and they'll all be stitched into this upstream band here, hoping to cover about 500 customers or so is typically what the cable system runs out and serves. So that's the upstream direction, and then basically to do the same thing, my diagram's a little bad here, so I'll just draw half of it, but they do the same thing downstream. It's the same modulation format, same sharing that's used. 1 over T is about 2 megahertz, and the 2-bit per symbol to get 4 megabits per second. Okay, so that gives you some idea. In this band, think of this as analog TV. I'm going to come back to digital TV shortly, but QAM is used there. If you get, I should call this 4, you get satellite TV instead. I don't have cable TV. I have satellite TV, direct TV. Again, uses QAM. This is coming from your satellite now down to you. And in fact, the symbol rate for these systems is 19.151 megahertz. And it's 2 bits per symbol. So 4 QAM or QPSK, sometimes called. So therefore, the rate is double that, or 39.302 megabits per second. And typically, they get 4 to 16 digital TV channels. On one of these slots. These carrier frequencies for these things coming down to the Earth are between 12.2 to 12.7 gigahertz. Each of these slots has about 24 megahertz.